the one on cell duality. And the paper was recommended to me by Andrea Tudor, who at that time told me that papers like that are written once every 25 years. And at that time, of course, I didn't know much math, so I couldn't judge. But it turns out that Tudor was correct. And in fact, the same could be said for many other papers of Nigel. So, humans are the only species in this universe who actually appreciate a good story, but they appreciate even more the presentation of this story. Sometimes, if the story is said many times and it's presented very well, and there are many followers, this story becomes a religion. And that's exactly what has happened with Nigel's work, and that's what we are here to discuss. So I give you a star round table, which includes Jorgen Andersen, an expert on quantization, Mr. Q. Gualteri, generalized geometries. Dan Fried, gauge theorem to Wolfsburg modular forms. Donagi, spectral coverings and legless program. Mr. Non-abelian Hodge theory, Carl Simpson, and Mr. Hitchin components, Oscar Garcia-Prada, and of course, I haven't forgotten, really, the star of the show, Nigel Hitchin. So we have wonderful moderators today, Carl Simpson and Oscar Garcia-Prada, and I let them lead the show. Oscar?
So I have another microphone here. Thank you, Emil. So let me say something that is obvious, but even then I'd like to say that the future of teaching mathematics is in the hands of so many people, a lot of people. Some of them have not yet been born. But of all these people working at the moment, we are just a fraction, a small fraction. And therefore, we are just expressing our opinions and some ideas that informally we want to discuss. And the role of this panel is really dynamize the discussion with everyone. So the thing is, each of us is going to make a brief statement, 3-4 minutes, no more, at least. And so about some problem, something. And then we may have discussion on the panel and then discuss with everyone asking questions. Yeah, do you agree? Okay. Yeah. We have 2 moderators because sometimes the moderator needs to be moderated. Okay, so who's going to start? Mr. Andersen, you sit here.
Okay, so I guess it's given what I have to talk about. I think that there are really some very interesting problems that concerns the moduli spaces and the ones without the Higgs field and the one with the Higgs field in relation to Chern-Simons theory. Because that whole story has never really fully been developed geometrically. So it relates closely to a T15 that we proposed in the beginning and recently integrated constructed combinatorially. But there are many questions about this that deserve a complete geometric description. For example, if I have a three-manifold that has a boundary on the surface, say a handle button, how do I describe geometrically the state vector on the moduli space, which is coming from the isomorphism we know there is for holomorphic sections of the moduli space to this T-Gibbs vector space. And so I could continue with many such examples where we simply don't have no nice geometric form in the release, and I think that would be super, super nice. Another problem is quantization of the expanded modular space. We really haven't grasped that yet fully. And that somehow has some very interesting relations to complex Chern-Simons theory, because that's really flourishing in the sort of combinatorial Chern-Simons community at the moment. There is something called AJ conjecture. It is some operators that kills and annihilates the state vectors that I just talked about. And I think there must be some kind of close relation to this SYC symmetry picture of constructing the analog of these what's called A-hat polynomials in that case. But then to round up and finish this, I also want to point out that there is a completely new venue of applications of this theory. And that is the advent or sort of flourishing of quantum hardware now. So I don't know if you know, but for example, any quantum program that you might envision with qubits and q-gates is actually a parallel transport of the Hitchin connection. All the parabolic moduli spaces. So that is a universal quantum computer. It is proven by Mike Friedman, the foremost topologist from the combinatorial world, and by James and my work, we know that as a multi-matrix parallel transport. So that's one thing. Another thing is many other new developments like quantization of time on space is something that I developed with Renato. We also know that is a universal quantum computer now. And so I really think there are tons of nice things there to start just using all of the knowledge that we have developed over so many years to apply to generate new quantum codes. There's a plethora of possibilities here, fantastic nice things. And just to finish up completely, I want to say that we are starting to do this at the center in Odense, and there are advertisements. So if you know some people who might be looking for jobs, please apply and have a look. But several of us are not really sure whether we're working on quantum computing or we're working on all the stuff we've heard about so far this week, and we will hear about the rest of the week. So these merge completely and melt. And so that is really fantastic and so fun to actually see that this platform theory that we developed a long time with very little applications is totally applicable.
My name is Marco Gualteri. I guess I'm the representative of the generalized geometry crowd. So generalized geometry has been around now for about 20 years, just a little bit longer than 20 years. And at first, well, we could discuss if anyone is interested how it originated, but after some development, after a few years of development, the first kind of turning point came when we realized that it was related to supersymmetric sigma models of physics, especially in dimension 2. And it turned out in a way that was unexpected, let's say, that it was the perfect language to describe the low energy geometry that emerges when you have supersymmetric quantum field theory in dimension 2. And as a result of that, it turned out to be related to mirror symmetry as well. And this is maybe not so surprising. If you look at Nigel's original paper, he explained how generalized complex structures could interpolate between complex geometry and symplectic geometry. And therefore, both the B and the A model physicists could be incorporated into one structure. That was only a hint of the future relationships to physics. And so that kind of evolved in that way. But the basics of the theory took a long time to develop, especially because of the small number of people that were working on the subject, but that has been growing. And we have in the audience right now several people who are really geometric analysts and who are now studying the geometric analysis underlying these structures like generalized Kähler or generalized Calabi-Yau manifolds. So that seems to have breathed new life into the subject, and also the structure theory of the subject continues to progress, especially because it turns out to be connected to the work of Weinstein. I would say that if that there were really two originators of generalized geometry, Nigel Hitchin, but also Alan Weinstein, and their work seems to have met in a very beautiful way, in a very unexpected way as well. And so all of the technology that Weinstein and his students have been developing has been very helpful in pushing forward the basic theory. So anyway, I look forward to hearing what other people in the audience might have to say about the future of generalized geometry, but it seems to be in its second wind at the moment, 20 years later.
Well, I thought I might talk a little about Dirac operators, which have played a large role in Nigel's work, dating from his thesis, as I showed earlier today. And of course, the Atiyah-Singer index theorem, which dates from the early 60s. So I was trying to think what's a forward-looking problem in that area. So the index theorem equates at its most basic level to integers. The one computed analytically from the Dirac operator, the other one computed topologically using K-theories. And in other forms, it's more elaborate. You're equating two elements of the K-theory group. Again, one computed analytically and one computed topologically. But we might ask for some geometric representative of the object in this K-theory group. After all, K-theory group is equivalence classes, something or different models. And you might try to construct something, an actual object from a family of Dirac operators. You might try to construct it analytically. You might construct it topologically. And then rather than proving that the isomorphism classes are equal, you might ask to construct an isomorphism. So a very concrete example would be to take a piece of that K-theory index, something like, say, the determinant or Flathian line bundle. So very concretely, if we have a family of surfaces, we can make a family of Dirac operators, say, coupled to a vector bundle. We can take a ratio and eliminate the tangential term and just have an index, which just depends on the, say, second Chern class of that vector bundle. And so if we think about the Chern-Simons theory that Jorgen mentioned, when people study that moduli space and study that line bundle, often it's said it's the determinant line bundle of that family of Dirac operators. But in fact, it comes to us more in the way I alluded to in my talk from Chern-Simons theory, with the much more elementary construction using differential forms. And the line bundles are isomorphic in the right ways, but what's an isomorphism? That's a very concrete first example of that kind of question. And I'll just say that the more general question, actually constructing a canonical isomorphism, analytic and topological index, construed as objects, right, would play a role in physics as well, in anomalies, for example, in the Green-Schwarz mechanism string.
Okay, well, maybe you should do it now. If you want. You get the rebuttal.
Yeah, yes, I was going to say, it's going to be hard to top that. Anyway, you've already heard 2 hours ago, I was talking about a whole bunch of different applications and connections of Hitchin system to various other questions in mathematics. One thing that I'd like to emphasize is that I think a lot of the importance of the work is from its connection to the physics. So yeah, there are things like the quantum stuff, but what historically was cyber-Williams theory that evolved by finding an integral system in a quantum field theory. And of course, that turned out to be an instance of the Hitchin system. And then there's been a huge industry that has evolved since that applies the existing system to various questions in quantum field theory. And I think it would be really good for mathematicians to talk about this and ideas for what can be done, what needs to be done. So I was talking with Nigel yesterday, and he was saying the system came in so many places could be a metaphor, but every integral system is a Hitchin system. And I was saying that I think the answer is no, because there's one other class that's really different, and those are individual systems where the fibers are Lorentzian rather than abelian varieties. They're maximum chloride, that was an indefinite polarization. And I think so there has been off and on work on trying to connect those two. So basically you want to go from calabials, which give you such systems, to non-compact calabials where you have 15 cycles, make the signature change. So there should be some differential view in non-algebraic direction of the Hitchin system. And I've seen various attempts, but nothing really convincing in the direction of that. That's a really interesting thing.
So Donagi Markman is of the second type.
Right. Yeah, that's an example of something that's strictly non-algebraic and yeah, they're just definitely polarized. So. And one last direction that I want to mention has to do with the three-dimensional symmetry and the related symplectic duality. There are many cases there where you get two different ways of describing an object or an object dual. And mathematically, they end up giving an unexpected isomorphism between two hypercator manifolds. Basically, you take one of them and you take the quotient by group G, and then the other one ends up being a modular space of something divided by a proper subgroup of G, and it can actually be isomorphic. And I think there's a big chance that the theory of Hitchin systems is likely to explain some of those coincidences. So thank you.
So yeah, so I wanted to start by sort of a synthetic comment, which I think is due to Richard, well, at least partly a really long time ago, which is that there's a whole lot of different infinities that are happening here in terms of for the Hitchin modular space. So you know, the Hitchin modular space is non-compact. The character variety is an affine variety, and also we see in the direction the base of the Hitchin vibration, vector space, so it's non-compact in that direction. And we've seen some talks about that. Also, the curve can be generic. So Ron, you were talking about that today. The curve or the underlying variety can be generated a singular variety. And although Ron did talk to the Hitchin system, I don't think we have a good control over the analysis. But that right now, off my third train of thought.
Several infinities, right? Several infinities.
Right, there's three. So the modular space is non-compact. You can degenerate the curve. But yeah, and the base variety can be non-compact. So in terms of the non-compactness of the base variety, we sort of understand that quite well now due to Takaro and Mochizuki's work. I think in that case, we still are missing a good understanding of, a perfectly good understanding of the moduli space theory for local systems or property bundles. Right. There's some constructions that have been made and so on. Exactly how those fit together when you vary all the data, the parabolic weights, the residues of the field and stuff like that.
still remains unclear. But so I think, what's really surprising, looking at this as a global, we know that organized conference look at this as a global thing, which is that how all the different possible directions kind of interact with each other. I don't think we really follow through just because there's such a large number of possible interactions on the different interactions. And in particular, the notion of twister theory kind of interacts with everything. And so I think that's a subject for discussion in the future. I should say the degeneration of the base variety. This was the subject of many conversations with Woodmill and Tony in the 1990s. I don't think we managed to say anything all that useful about that. So that's a question. But for example, the relationship between the W. I'm sorry. The relationship between the WKB theory, which happens when you go to infinity in moduli space, in Hitchin moduli space, and for example, degenerations. I think that would be an important question, which is really pretty much completely untouched as far as I know. And as I said, I think the twister theory comes into this picture in ways which need to be investigated. So.
Yeah, so I'd like to single out 2 or 3 directions, all connected to the moduli space of heat bundles on inner surfaces. The first one that is originated with the beautiful work of Nigel in the Hitchin component, and that has give rise, as you have seen in the talks by Alan Inghart and Steve and Brian and others, the emergence of higher technical theory, right? And bringing where now we are in a wonderful, I think, beautiful situation where after 3 decades, basically, there is a classification of what are these higher technical spaces for surfaces, for complex surfaces, maybe even for non-complex surfaces also. And so a lot of work to be investigated about the geometric significance of these higher technical spaces, and also as in the exploration that Brian was explaining today, how in particular heat bundles or in the heat bundle fixation can we grasp some properties of the representations, right? So that exploration is I mean, that area is not a new area somehow, that I anticipate a lot of work and very interesting things to explore. In relation to this, actually, some very intriguing relation of higher technical theory with another different area, which is the area of Bridgeland stability conditions in Carlos' work. We've been at one of that kind of change, and I'm very intrigued whenever I hear some talk about Bridgeland stability conditions and the complex manifold that they are. You have the feeling that this has to do with technical theory, and we see that actually the theory, but also with higher technical theory. So that's very, I think, totally. We have seen the beginning of the iceberg. Right? So another connection of direction involving these bundles is more in relation to the talk of Gold, Shaw, and Ron, in particular, having to do with Hitchin vibration and with Antamash, of course, and also the mirror symmetry, but also in particular the different generalized Hitchin vibrations that Ngor was mentioning, that brings very intriguing questions and link to generalizations of the geometric lanterns program, which that somehow connect not just one group and Stewart, but some spherical variety and something else. And, so those are some of my favorite directions, and we also need this. I mean, but the question about integral systems and whether every integral system is Hitchin. In fact, there are many integral systems that come out of this multiplicative Hitchin Higgs bundles that Ngo was mentioning, and so that's also and the relation of that to monopoles that has been explored, and there is a lot of things to understand. So, well, I think that those are the directions. I think maybe so Nigel can tell us something. We have missed many things, many directions or areas that we may want to.
No, well, actually, I thought maybe I could.
I'm afraid.
Oh, really? Yes.
Well, maybe we can kind of gain some information about possible future developments by getting momentum by looking at the past. So maybe I can just describe, if you like, the origins of the 1987 paper, because it's in a way, this is the way we all do mathematics, I suppose, that sometimes we respond to challenges or given a problem to solve. Sometimes things just show up, things are just purely by chance. But in this case, I think it really goes back to the 1977, the instant-on problem. This was something which was given to us. Singer came to Oxford and told us about gauge theories and self-duality and so on. And somehow that changed the way I was doing mathematics a lot. And so, gradually this was a problem in 4 dimensions. And then once we'd spent some years on that, I started to look at the corresponding 3-dimensional problem, that of magnetic monopoles. And in doing so, that was where, for me, the spectral curve, this was a spectral curve which was involved with actually solving the equations, the problem on the equations, through twistor methods. So that was my first experience, if you like, of spectral curve methods. And then, in particular, after NARM came in, the NARM transform, then this spectral curve, which I described in one way, became spectral curve for in more sort of integral systems setting, no, perhaps not in the symplectic setting, but you have a polynomial, a matrix of polynomials, and you have the isospectral deformations of this, the corresponding lattice equations and so forth. So, this was kind of experience which was relevant to what I was doing at the time, but which kind of was there in the back of my mind and so on. And then, so it was by doing monopoles that, while I was doing monopoles, I came to, I spent a year in Stony Brook, and I thought I was going to do monopoles there, but then Martin Rocek was there, and Lane Lawson had told me, well, he's doing something interesting. And then this is when we had this hypercable quotient construction. I can't resist mentioning something that Lester pointed out to me, that something I've never noticed, I don't know whether any of you noticed. It's this paper called Hypercable Metrics and Supersymmetry, and it's by Hitchin, Carl Hader, Lindstrom, and Rocek, HKLR, and it spells hypercable. So there was this hypercable quotient construction, and then when I came back to Oxford after Stony Brook, then Gualteri said, let's use this in an infinite dimensional context for the moduli space of monopoles. So then we found a formula for the hypercable metric on the moduli space of 2 monopoles. And so then, after that, I began to think about what I've done in 4 dimensions, 3 dimensions, what happens in 2 dimensions. And so to start with, I was thinking, all I wanted to do was to find a hypercable quotient construction in infinite dimensions, which would produce a hypercable metric on the modulus. And at first I thought it was just going to be the cotangent bundle and modernized space of stable bundles. I mean, that's. But then I realized that there was more and more to it. But then, to be honest, the integrable system was a sideshow. I mean, in the 1987 paper, it doesn't play a particular role. And it's just that somehow there's a section on it. I mean, just in rank 2, because that's all the paper did. But it was as I was writing that paper, all sorts of things started. I realized all sorts of things that you could do with calculation of the topology, which was kind of modeled on TF1 and so on, and then so it's I'll be honest with you that I was having a big argument with my wife at the time, and I had a lot of time to actually concentrate. Every time I went to my office, something new appeared, but so this was the chance. So maybe, if you like, there was momentum over all these years through instant bonds and monopoles, and then picking up these other ideas, spectral curves and so on, that they kind of really found a home in that paper. So anyway, that's so some of these things, right, were pretty random, and okay, so when it came to the other 87 paper, this was the Newton one. That was done in a hurry in a way, because so Miles Reed told me to, that I should write something for the manual volume. And I didn't have the analytic support for the Higgs bundle itself. I hadn't got Carlson's work. So I had to kind of rephrase everything in terms of cotangent bundle rather than completing it in this sense. But that was okay. I was doing that because Miles asked me to do something. But then it was just, in a way, anybody could have done it, because it's just once you see that the numbers add up, it's there for the taking. So that was happy for me, but it was almost pure chance. But of course, it did link in with what I've been doing. Okay, so that was the kind of history. As to problems for the future, well, there are a couple of things which really bother me a little bit. Or three, I suppose. One is this question about, which relates to Brian's talk, really. How can we go from the Higgs bundle picture, the analysis of these equations, to actually understanding what the representations, what properties those representations have? And at one stage, I think I tried a student to look at degenerating the curve, taking a closed curve and changing in the Riemann surface, changing the complex structure by squeezing that down, and hoping that asymptotic form of the solutions to the equations might actually reveal some information about the holonomy around that little curve. Actually, he told me that all the inequalities were going the wrong way, and then he left mathematics. But this is, I think there's a possibility there of something. Somebody with the right analytical tools, really just, there must be some relationship between the holonomy and the sort of the behavior of the solution to the equations as you squeeze that down. And it also, in a way, kind of relates to this great work that we heard from Carlos about Ron and Tony's work on this, the Hector eigensheet and so on.
It's Carlos too.
Yeah, it was you apparently.
Yeah, well, we had Carlos, yeah, sure. Because this is supposed to have some number theoretic consequences, and so how is it that we can rely on the analysis, on the Mochizuki's work, and so on, to get something which has relevance maybe in characteristic B or something like that. What intervenes? What is there? And again, maybe degeneration is the answer. Maybe it's like, you know, maybe even a tropical version of its bundles or something will have a point of contact between the two. It's again, it's a little bit like the original theorem about actually using the solution to the Higgs bundle equations to get the flat connection. I mean, I guess it was Whitman who told me, he said, well, you know, isn't it kind of obvious that if you have this spectral curve in the cotangent bundle of the Riemann surface, this is the Lagrangian, you're intersecting it with the fibers of the cotangent bundle. Well, the fibers are Hamiltonianly diffeomorphic. So, you know, floor theory would say that we can identify the spaces on the intersections. So clearly there's a flat connection on this bundle.
Yeah, I've heard consider say the same thing.
Yeah.
Clearly, you can do that.
Clearly, you know, how is it that they say that we do that, and we rely on the complicated partial differential equations to do that? There must be another way. But let me just say finally that the one thing I've had 2 students work on this with some good results, and this is something which bothered me right from the start. Right? So the first one thing which I really liked myself about the 87 paper was that it gave a different proof of the uniformization theorem. That I started with something generic, and then you solve these equations. Then in the limit, you find that if you have the right limit, you find out the solution to the same. You get a constant curve geometry. So this is another approach to uniformization. And so, but what it means in terms of Higgs bundles is that the structure you get by uniformizing, classical result of that uniformizing the Riemann surface can be phrased in terms of a Higgs bundle. But then there's this process of this norm transform. So you solve the Dirac operator coupled to the Higgs bundle in the right way. Then you can transform any Higgs bundle to a hyperholomorphic bundle on the cotangent bundle of the Jacobian. And so there's something on that cotangent bundle on this flat hypergamma manifold. There's a certain hyperholomorphic bundle of that which corresponds to uniformizing the Riemann surface. What is it? Well, here we're looking at, we could use the twisted theory that Carlos has been talking about. I mean, a hyperholomorphic bundle is just the same as a holomorphic bundle on the twistor space. So is there some way? So this is like saying that uniformization is something to do with holomorphic bundles on a complex manifold. You know, how do you characterize them? Is there some way in which you can say what kind of holomorphic bundle this is? It's capturing the information. You know that from the work of my former student Johan Bonslow, that you're not losing information in this direction. So it seems to me that there is, if you want to have the right language to describe these transforms, then there'll be a very satisfactory situation. Uniformization appears in this holomorphic category. Anyway, those are my long-term wishes. I'll never do it myself. No, perhaps somebody.
You're not suggesting that we should have a fight with our spouses, right? Right? No. Yeah. Now seriously, I just want to make a comment.
In a university environment.
But the last thing you said is kind of something you can expect, right? Because the uniformizing solution is a solution to the Hitchin equations, and these are dimensional relations of
instantons. And if you think of the original twister correspondence, I mean, it's just lovely, right?
Yeah.
These are polymorphic frontals on the twistor space, right? So it's very natural to respect this, of course, in different, manifesting in a different way because of global. Yeah.
But that's right. So whereas in, for instantons and monopoles, you can do the twistor theory on the space itself, the relationship with the self-Young-Mills equations is only local. Once you wrap things up onto a real surface, it can be local, but the substitute for that is the use of non-transform for something which is flat way.
So, are we done with the initial? I thought maybe we could just like have another round of discussion of the panel, and then we'll ask people for comments from the audience.
Could I ask a question?
Yeah. Yeah, I think that's a question.
I have a question which might be of interest to everyone, to Nigel, which is, after you wrote that paper, let's say in the early 90s, I'm curious, from your point of view, what was the reaction of the mathematical community? How were you treated at that time in comparison to, let's say, 15, 20 years later? I'm speaking of the Yang-Mills paper. I'm speaking of the 87 paper.
Oh, the 87 paper. It didn't have much traction, to be honest. I did catch, actually, most of the reprints that I got for that ended up in Kiev. A group of physicists and mathematicians in Kiev.
I got one, yeah, that's one, so.
Yeah, there are a few left. And yeah, some physicists noticed it. I remember I went to Venezuela actually, and some people there were interested in it, but it was some time before it really got recognized. Yeah. I think, I mean, my memory serves me right. Yeah.
This is something I actually got a reprint when I visited you in 1987. I was still just a little student, and I was still at Rice University for transfer, and I brought that paper and I put the whole department to work on the paper for a semester. So and the reactions in the product line and some cool, they're very excited to be one.
I was also great.
No, I actually I had heard also now from people at the Tata Institute that Andersen recognized there's something there worth working on. And in fact, that's when Nitsure changed the methods to blocks to do a proper version, I mean, algebraic geometric version.
Can I make a comment?
Yeah.
From my point of view, this is just my own personal point of view, but it seems to me like the thing that made that paper so important later was two things. One, the side written solution, which immediately then physicists got interested in Hitchin systems. And then later, Lavery's connection of the Hitchin component, to actual interesting representations, discrete variables, sort of two injections, both from the physics side, both from the mathematics side, and that seemed like there was an enormous revival interest in both of your 87 papers towards the late 90s, especially in the 80s. I think
When you were saying that early 90s,
right, exactly. Yeah.
So yeah, I think Marco was talking about that early 90s.
Right. I was wondering about I understand that the Tata Institute and some smaller European groups were interested because it was in their wheelhouse, but somehow I think what you're saying is very clear that there was a revival in the late 90s, and then when Witten and Kapustin's paper came out, there was an even bigger explosion of interest in that original paper. Is that something you also felt?
Yeah. Yes, certainly. I mean, I should say in the early 90s, I was doing other things as well. There was the different signature version. There was a paper on the harmonic maps from two torus into the sphere. And I was doing stuff with Einstein metrics and Annabelle equations. So some of the things that, yeah, so that's right. So somehow the
Teichmann space paper was a bit of a one-off, I suppose, at that time. But anyway, anyway, I had other things on my plate also.
One of the other standout things in that paper was that it constructed a hypercade manifold. That was an early example of that. That's interesting. Did that not, was that just too ahead of time to generate much interest?
Yes and no, because actually the finite dimensional hypercade quotient was being used quite a lot, you know, so I'm trying to think about the time scale, but when it was HKLR was in, well, it took a while for that paper to come out, but the actual method was there in the mid-80s, and so I think people were happy constructing hypercade metrics by finite dimensional quotient construction. But it was really Attia who suggested that we should use the infinite dimensional version. I mean, of course, he looked at Yang-Mills' theory on Riemann surface from this infinite dimensional point of view, and I guess also Taubes had pointed out that the kind of linear quaternionic structure on the monoform and moduli space, but to say that to use this as a method for, you know, constructing moduli spaces with hypercade metrics. That was, but then of course then you get all this other stuff coming out, the different complex structures which have to have a meaning. I guess was looking back, it did make it part of the point. At first I thought we have a hypercade metric. What are the other complex structures? You know, so you look at the equations and then you change the I to the J, and then suddenly you see a flat connection. I can't recall that that's exactly how it went, but I think it was important to try and understand this. I mean, I think I first gave a talk about that before I had the full Higgs bundle picture at in Mexico, the Lefschetz Centennial Symposium or something like that. When at the time it was simply something on a neighborhood of the zero section in the cotangent line of the butterfly space of stable bundles. So I probably, even at that stage, I haven't looked at the paper, but it may be that the link with the track connections wasn't apparent.
But I can't resist commenting on something that had a big impact, I guess, on Stephen Newton, because in your paper you have other objects that appeared. These were vortices, right? That appeared as fixed points, and you brought the problems of, you know, the comments to connectivity and how this, you know, that was a problem in itself.
So I was thinking of, I mean, everybody's free, of course, to say whatever, discuss whatever you want. But just like to get to the question started, I was wondering whether there were any comments on the general theme of mirror symmetry, which I think is sort of behind a lot of the things that are going on or maybe going on in the future. I think having all the different areas. But I mean, that's one possible thing, but maybe we should just have a start with the discussion and Jorgen, if you want.
Yeah.
On that topic, or any other topic if you want.
Well, I tried to mention it a little bit when I said something. So I really do think that one should try to look at the Lagrangian or flat connections, complex ones that extends over a handle body. This is some kind of ring in your systems set up, and do that on the dual, and then somehow that's supposed to be the B module, which acts on these sections on bond G. And I can't help having the feeling that that should somehow be the quantum equivalent, somehow done the right way. And this quantum equivalent is sort of very difficult invariant to get hold of in a very concrete way in the quantum topology. We know that there's something called the AJ conjecture that says that the limit as a certain quantum parameter goes to H bar goes to 0 is the classical A group. And so therefore this A hat invariant is a super interesting invariant. It's sort of related to the fact that we believe that the Jones polynomial determines the volume of the knot. And so I really encourage people to try to move in this direction. I think there could be some fantastic interaction between quantum topology and then this side. And let me take some inspiration from the scaling models. The scaling models are linked closely to the big version of the modulus with black connections already. And somehow there is a close relation between the scaling module and then we say head invariants. But I think that of course this would not default disorder and there is this beautiful construction of theta functions using counts of pseudo-holomorphic curves. And I would love to see something like this done on the moduli spaces of flat connections. And actually, do people know what is the mirror of the moduli space of SU2 flat connections?
Yeah. In the simplest case, when it's intersection of two quadrants in P5, that's rather clear. It's one of Ginsburg model, which has three singular fibers. One looks very much like the fractional curve, genus 2 curve, which comes from the conic bundle associated with this funnel, and then there are two other singular fibers.
I really would like to see this done sort of over the entire family of Riemann surfaces, every moduli space there, not just the cases where it's hyperelliptic. But did I understand correctly that the D module that you have mentioned as a mirror of this Lagrangian, you expect to be related to the scaling module? Yeah, in some way it should, but okay. Because it's a vanishing idea inside the scaling module of that end. So the scaling module done the right way is supposed to be the endomorphism theory of the vector space from T to T. And they say that it's supposed to, in its more supposed geometric version, it's supposed to be some operator in the endomorphism. Maybe allow me one more comment about quantum computers. So there was just so that I can tell you that community is also aware of the work that we're doing. In summer, Quantinuum came out with a paper, and in order to demonstrate that they really had non-abelian anyons, which are very important for a certain topological quantum computing, what they did was that they implemented a surface code that does a digraph reading T curve T, so that's a T curve T for finite groups T4. And what they showed was that they computed a link invariant with this quantum computer, and it gave -1. And so if any abelian theory would give 1, so this was a clear indication that they have non-abelian anyons going on in this code. It's not the universal quantum computing. They weren't aware of that. We told them that. It's because the image of the market class group inside the vector space is finite, so that of course it cannot run dense in unit terms. But the theory we all like and love here, and people that made it in the audience and work on, that is universal. So just please use all those fancy geometry to generate nice codes. There is a complete deep need for creating new quantum codes. We know very few codes that are smart. We need to develop more of them. Anyway, that is the key program.
So mirror symmetry, I think, had a lot of overlapping interaction with generalized geometry, especially for generalized complex geometry. As I said before, a generalized complex structure that allows you to interpolate between a complex and a symplectic manifold. And mirror symmetry is really, as Kontsevich developed it, in the mathematical sense, it's an equivalence between categories that are associated to a complex and to a symplectic manifold. And so one of the motivating problems in generalized geometry, at least in a simple case where we're dealing with generalized complex structures, is the following. It's saying that if you take a complex manifold and look at its deformations as a generalized complex manifold, it includes the well-known complex deformations, but it also includes what we normally think of as non-commutative deformations. So there's a sense in which if you take a complex manifold and deform it as a generalized complex manifold, it moves into the non-commutative direction. And it doesn't do so infinitesimally, it is actually supposed to be non-commutative. And this is an idea that has never been fully realized. And I can say a few comments about that. On the other hand, if you look at the symplectic case, symplectic manifolds are in a sense generic, meaning that if you deform a symplectic manifold as a GC manifold, it remains symplectic, except for the possibility of adding a B field to the symplectic form, so that now you have a complexified symplectic form. And there's been a lot of work in the A model. My favorite work in that direction is the paper of Oru, Katsuoka, and Orlov, where they took a symplectic manifold of the surface and added a B field to it, and then computed the Fukaya category for that, showing that it was actually equivalent to the category of sheets on a non-commutative deformation of P2. Again, this is a strict deformation quantization. It's not a formal statement. Right? So but in any case, the idea is supposed to be that any generalized complex manifold should have a category associated to it, a category like the category of coherent sheets, or maybe the derived category of coherent sheets. And this category remains somewhat elusive at this point, although we have some proposals for how to build it. And I think that the main reason why it remains elusive is because the mathematical community, or at least I should speak for myself, I am reluctant to really take seriously the entire sigma model and its quantization, because that's somehow the only route that we have available to us at the moment for obtaining what the physicists claim or what they predict. So I don't know if we will eventually, study this genuine quantum field theory of maps of a two-dimensional surface into a GC manifold, but somehow hidden in that ill-defined theory is the possibility of having such a category, which could capture this kind of non-commutative behavior. And in any case, these categories would supposedly participate in mirror symmetry, meaning that just in the same way that a complex and a symplectic manifold are related by mirror symmetry, so too would the deformations of a complex manifold and of the symplectic manifold participate in mirror symmetry. And so this is something that physicists are incredibly confident about, and they have not changed their story for more than 20 years. So it's probably true, and yet we continue to not have a full understanding of this category. And I think that maybe there are some groups here today that are working on this problem, but that surely is in the future a subject.
Well, maybe a general comment about mirror symmetry comes from this automorphism of symmetry algebra of certain supersymmetric theories. And thinking about supersymmetric theories, for example, the one that gives the Donaldson invariance, there are typically more fields in those theories than we tend to use in geometry. So there's more than the connection. And for various reasons, they don't occur, for example, in studying the self-fluid equations. But when you get a manifold with b plus equals 1, then suddenly things are a little bit different there. And so there's more in these supersymmetric theories, in particular, more fields. And I've always wondered if they would say something about geometry in various forms, if we use more of those fields, and I've never been able to think too productively about that idea, but it's still kind of out there. So that's something that also outgrown morphosm with academics.
Well, mirror symmetry is, and its relationship to the duality between its level and other spaces. Language dual is fascinating collection of conjectures, and it's very rewarding to see when, as you make some small progress, to see if it fits in with this picture. That's what partially why Tomas was held so excited in his search. We were kind of innocently pursuing something, and then suddenly we saw that actually the homology of some homogeneous space for the language dual group was making sense in doing Hecker transforms of the on this Hitchin section of the moduli space. So it's a kind of, I mean, to me, it's a guiding principle, which in some respects, I don't, you know, what we're told as mathematicians by physicists is sometimes a very refined version of what's really going on. So if they'd told me that a BAA brain is going to go to a BBB brain, and sometimes you see that it works, and sometimes you see that it doesn't work. At least if you interpret it in a naive way, which is the most obvious way for a differential geometer, about Lagrangians going to hyperholomorphic bundles, and then one has to have some degree of skepticism about that, because there seems to be far more on one side than the other. That's somehow just because they're perhaps making naive interpretations of what's going on. But as a guiding principle for understanding the internal geometry of these moduli space, it's very exciting sort of thing to do.
I guess we don't have much today, but I had an anecdote when we got when we formed the group to supposedly study neurosymmetry 8 years ago. Immediately the first thing that came out when I was on the day was to connect neurosymmetry with homology. It's the natural way to work that hadn't happened.
Which homology?
No homology patterns.
But you have a feeling as to why that you don't know how to do that? Although people say they're like, I know what thing that this is just the opposite.
Yeah, I think it was one of those things where the intuition is created, but there was some detail.
So I'm not a big customer.
Well, just one obvious comment, as Nigel said, we get these refined versions of these conjectures for these statements from physics, but a lot of these statements are purely quantum, really. And it's only, these quantum theories typically, but not always, the 2-0 theory that was mentioned, but typically they come in families. And it's only asymptotically in these families that we can see classical geometry and then make our statements. But often the statements really lie somewhere else. And that's a piece that we really do have to keep in mind, this quantum piece. Like, it's really where a lot of these statements lie.
Well, I just have a small comment, but this is something I don't know this, but I'll leave about it. I'm kind of wondering whether there's some kind of mirror, there might be some kind of mirror symmetry between the character body and the hidden bundle moduli space, for example, or the moduli, the Durand moduli space connection. I wouldn't know what to say about that. It's just that there's some statements to the effect that the Betty moduli space is a large LaBiA. So that might sort of be playing roll or non-compact, like beam size and a symmetry, that sort of thing. But
Well, I think I'd like to really invite the all of us to make comments and to make suggestions to your favorite development problems, etc. So please,
maybe we can go and pass around.
absolutely, that's amazing.
We'll take one half of the room each. If I don't want anybody like to make comments.
Yeah, but maybe I would say a few words because Marco, I think, sort of alluded to some of what I'm doing, I think, and other people. So yeah, I should say I have been working a lot on generalized scalar geometry, and my talk on Friday will be entirely sort of within the confines of generalized scalar geometry, but I sort of came to it in my own way. I started this program with Tian trying to solve the classification of complex surfaces by a Ricci flow type of argument. And we sort of very quickly found, once we found what seemed like the right equation to use, that it had some connection to generalized scalar geometry, and I had no idea what it was. We found this connection. But then sort of the farther I go with this PDE, even sort of outside of the generalized scalar setting, it still has something to do with generalized geometry. And sort of the farther I get with this equation, the more it's clear that it's sort of very intimately linked with generalized geometry, and sort of all of the progress seems to be linked to this. And as far as sort of looking to the future of Hitchin mathematics, the sort of glimmer in my eye of how the story will finish is that of this program of trying to classify complex surfaces is that all of them are in a certain sense that sort of all of the long-time geometries, all the long-time limits of the flow that we see are in fact generalized scalar. And I think this would be a wonderful end to the story. Nothing would make me happier than if that would happen. It seems to be, there's some evidence in this direction, but well, it's just a conjecture.
I don't have a specific remark. I just wanted to say how wonderful this session was. So one of the most interesting sessions. Of course, future of mathematics is always interesting because it's so mysterious and we don't know how it will develop. But that was extremely interesting. Thank you very much.
No, go ahead. Thanks. So I am the aid agent guy. So I wanted to mention, as I said in my talk, right, the AEGM, I think it's really a turning point in lots of stuff that we've been doing the past 50 years. But and this is, to my knowledge, maybe Nigel can shed some light on it. It's really when gauge theory, that was something that was being developed by physicists since the 40s, since the 50s, sorry, became a math subject. So it was this point that it became a math subject, and the Atiyah-Ward correspondence and the aid agent construction, it's perhaps the first deeper link between math and physics. And that is followed later by the Hitchin-Kobayashi correspondence. There's another very deep link between physics and differential geometry and algebraic geometry. And it's two constructions from the late 70s, early 80s that gave a big boost to algebraic geometry as well. That's my opinion. I don't know if other people here agree with this. So maybe stability of bundles was something interesting to a few algebraic geometers, starting with Mumford, but this link with physics via the aid agent construction and the Hitchin-Kobayashi correspondence, brought a lot of attention to study stable bundles on surfaces and also on trefoils. And this is, in a sense, like again the frontier of
some of the things that I see, right? So there are recent papers and recent efforts in trying to understand what would be the Hitchin-Kobayashi correspondence for regional stability, right? So what are the differential geometric side of this outright story of the regional stability? And also understanding, starting studying this particular class of bundles on B3, right? But then if you and the modular space of bundles or sheaves on B3 and other threefolds is a very complicated variety. It has many connected components, many reducible components, and if people know how to count components of the Higgs modular space, I don't know if anybody knows how to count components of bundles on threefolds. Right? So it's not known if this is connected, not known if this is how many reducible components it has. So there is some direction to be pursued there as well. And this ties up, right? So it starts with stability back then in the 60s, goes to physics. Physics gives regional stability, comes back to mathematics, and goes back to physics again, or PDEs. So this is a very interesting developing story that Nigel played a crucial role in its beginning. Thank you.
Thank you very much.
Well, so what you just said sort of reminded me of some idea that I had in the paper, but I couldn't get anywhere, and it's related to something that Dan was mentioning, namely that the Atiyah-Singer index theorem is in a sense a very linear theory. It is telling you that the index, computed topologically by just counting dimensions of vector spaces and doing various things with this, can be given topologically. But I think if there was a nonlinear index theorem, that would be super interesting. So something that would say that if you have to compute a number of solutions to some PDE, and you would like to count how many solutions there are, then that would say, well, there are some nonlinear characteristic classes, and that those classes will evaluate somehow to this number. An example of this is these Donaldson invariants and the Cronheimer-Roth classes that they devise and that was further developed by cybernetic theory. That's an example of what I'm thinking of, where you can really get your hands on these numbers, because these are typically very, very hard questions, and they are questions that are really interesting from a physics point of view. And the other question I had, this was to Nigel, and you were mentioning that there were certain coincidences that somehow led you to various things, and I was just wondering if you could comment a little bit on this geometric quantization paper, because it also tied in with your integrable system, right? And so I think it must have been somehow a revelation to see that actually that thing could exist and it was actually projection in the flat and that everything just fitted together in this very, very special case.
Yeah, that's true. That was serendipity, really. I mean, I knew about these things, but I guess the question was there. I mean, we're talking about quantization topics from, it's around because of Jen Simons and so forth. But really, it came down to the fact that I didn't understand what a theta function was. I mean, I guess I understood it in the sense that I understood it, just classical theta functions. I understood it in terms of sections of the line bundle on the big variety line. But then and also I understood that in terms of the formula for that. But then the question about why there is a flat connection on the space of theta functions. I didn't realize what was going on until I actually came upon this paper of Gualteri's, where he gave a very, very nice algebraic geometric description, which involved
holomorphic heat equation. And now, of course, then I said, well, of course, I know heat functions satisfy heat equation, but this looks like this is algebraic geometry. And then, what is the symbol of the heat equation? Well, it's the symmetric tensor, which goes with the variation of the structure and the variety. And then I thought, well, I know about symmetric tensors, because that's what I was writing about in paper. And so, that was pure chance. And then, put the two together, and there was a heat equation, the well-defined heat equation, which then the Russell brackets being 0 and flat. So that was pure chance really, except the problem was there in the air. I was thinking about the problem a lot. But I think the point was that I didn't realize that the standard way of parameterizing theta function is to deal with the fact that as you parallel translate, that goes along with it. Not that you take products of theta functions to get products of sections of line bundles to get sections of line bundles together. That's a more complicated relationship. But so it was a question of my somehow not understanding the context of a lot of very classical mathematics and seeing it in this modern setting in the working way.
I think that there's now an opportunity to actually complete this picture and to try to understand. So how do we try to use this Pittsburgh model to produce the analog theta functions for SU2? Yeah, to produce them. I mean, so somehow we have this very nice paper that describes that classical theta functions are really just. This is an instance of Maxim's nearest symmetry rolled out completely, right? That you have formally for the theta functions, which just are counting suitable of the curves on the mirror. So you can see this, and this is the instance of his homological mirror symmetry. And I think it's begging to be applied for the SU2 quantized space and its mirror. There was B side on the SU2 quantized space, A side on the Pittsburgh model. And just see that we can really count the curves and get a nice formula, and it's parallel perspective.
I'm going to ask a somewhat provocative question. So, the Yang-Mills equations have been a great source of inspiration for the years, but of course they came out of the standard model. So, with all of the things that we've learned over the years, we've come down from dimension 4 to dimension 3 to dimension 2. We're working our way back up with things. Are we going to get to understanding the standard model?
Standard model. The Yang-Mills equations actually came in 1954. Yang-Mills were, I think, at the IAS, and one of them was living next to Raulerbach, but they only talked about gardening and didn't talk about the Yang-Mills equations, the connections that happened later at Stony Brook, Jim Simons, and so on, and Yang. But are we going to understand the standard model? Well, I don't know about that. Are we going to understand why there's a gap, for example, in pure quantum gauge theory? That would be nice too. But I don't know. Again, these are quantum problems that seem a little bit far away from this kind of geometry. One comment I will make along those lines is that, in a sense, the self-dual instanton equations in 4 dimensions were the mother lode, from dimensional reduction, which we've been talking about, and generating all this beautiful geometry in low dimensions. And there was at least a vision, and I think partially is playing out, that this 6-dimensional theory, this superconformal theory, 2-0 supersymmetry, which we're not, interacting case is really an isolated theory, so it doesn't come in these families where you have a classical limit and you can make a description in terms of classical geometry, but somehow those theories are also, through their dimensional reductions, quantum generating all sorts of interesting low dimensional geometry. So they appeared, for example, in four-dimensional theories that appeared in Ron's talk are examples of reductions of that kind of theory. There are all sorts of reductions to three dimensions in relation to Chern-Simons. So all sorts of things are flowing now from that quantum theory. But whether all of this, that's of course involves a lot of supersymmetry. The standard model doesn't have supersymmetry, and so yeah, so there seems to be a little bit of this.
Well, another question related to what you're asking is, in a sense, more fundamental. Will we actually soon learn how to do path right? Because that's a huge technique that's developed in physics, extremely successful over there, yet we still don't know the mathematical definition of these objects. And, you know, researchers, I think, will play, potentially has a lot to say in this direction. And actually, researchers points to geometric objects over Riemann surfaces, which are very, very similar in nature to Higgs bonds. They might be more complicated than Higgs bonds, but there are certainly some cases where they are just Higgs bonds. And so I think that there's some very interesting interactions there that we haven't really gotten to the grips of, and that will just develop, I think, quite soon. So, yeah, I think it's moving forward. But I think that the key word is to try to understand that. Maybe.
Yeah, just wanted to mention regarding the standard model. So there used to be a great hope that you can click through the shades and get a lot of information about it by starting out from quantitative theory or from string theory and of that. And I think that that's still alive. You can save a lot of work by getting specific models for the standard model in terms of specific quantification, quantification of various string theory.
Maybe I'll convey. Ed Whitten once told me that this is not again the standard model, but pure Yang-Mills, is much simpler. That every time something new comes up in physics, whether it be string theory, there's various limits that we want to do, there's all sorts of things, he immediately tries to see if there's a gap in the pure in Yang-Mills. So far.
Can I just comment that although we were in the process of solving the equations that govern the universe, we can still hope that the best might possibly be. Yeah, so Oscar, yeah. So I think Rich will be good to close this discussion. So thank you everybody very much for all your participation. Thank you to the panel members. Thank you, especially thank you to Nigel for giving us the opportunity to have this discussion and also for great participation. So